this video, we're going to continue our discussion of finding the area area under a curve. We looked in the last video at doing that geometrically and the meaning of a definite integral. In this video, we're going to continue that discussion, and we're going to continue talking about finding or evaluating a definite integral geometrically. But in this particular case, instead of counting blocks, we're going to use rectangles. But first, we're going to start with the warm-up. If you're in my class, I would encourage you to stop the video, to try the warm-up, and then resume the video. In problem number 1, we're finding the antiderivative of cosecant cotangent. So you have to ask yourself the question from trigonometry, what function has a derivative of cosecant theta, cotangent theta, and that would be negative, edit, undo. Okay, let's grab a pen here. So that would be negative cosecant theta plus c, a family of functions that differ by a constant. Number 2, from our discussion from yesterday, what does the antiderivative from 0 to 5 of v of t represent? Well, remember from our discussion yesterday, we are evaluating a definite integral, so we're finding the area under the velocity curve, and we're finding the net area. So from our discussion, we should know that this definite integral represents the change in position. You could also use the word displacement there instead of position. The change in position measured in feet, because when you integrate a rate, you lose the rate. So if we find the antiderivative of feet per second, that takes us back to feet. The change in position measured in feet from 0 to 5 seconds. Number 3, the function graphed below represents the velocity, v of t, in miles per hour. So this is a velocity function. It's measured in miles per hour, and the time is in hours. A particle is traveling along a horizontal line. Write an integral. I'm on letter A. Write an integral that represents the distance traveled. Now remember, distance traveled, you have to make all of the negative area positive. So if you take a look at the graph from 0, so 1, 2, 3, about 3 and we'll call that 3.5. From 0 to 3.5, all of the area is above the x-axis and positive, and then from 3.5, that would be 4, 5, about 5.5. From 3.5 to 5.5, so let's go ahead and mark this on the graph. This is about 3.5, and this is about 5.5. Let me make sure I counted that correctly. 1, 2, 3.5. Okay. So write an integral that represents the distance traveled during the first 3 hours. There are 2 ways to write that integral. We can go from 0 to 3.5, v of t dt, because all of that area is positive. Then we're going to subtract the negative area, forcing it to be positive. So we go from 3.5 to 5.5. v of t dt, which is the same thing as going directly from 0 to 5.5, and we can take the absolute value of velocity to force all of that negative region to become positive. So either of those, you should be able to write the integral with or without absolute value. All right, letter B. Approximate the distance traveled during the first 3 hours. And at this point, you would simply count blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll call this 10, 11, 12. It's a little bit less than 12, but just for, well, actually, it's not, because we picked this up. So we'll just, for simplicity's sake, and to get a whole number, we'll call that 12. And then in the below the x-axis, we have 1, 2, if we put those together, let's call it 3. So approximate the distance traveled, so that would be 12 minus negative 3, which will give me 15, and my units are miles, 15 miles. Oh, actually, I didn't read the question. First 3 hours, let's back that up. I did the whole thing. So during the first 3 hours, 1, 2, 3, it stops here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's about, well, I'll call it 12. It's a little bit less than that, but just for simplicity's sake, about 12 miles. When is the particle traveling to the left? Remember from our prior experience that a particle travels left when velocity is less than 0 and travels right when velocity is greater than 0. So the velocity is less than 0 from 3.5 to 5.5, and the velocity is greater than 0 from 0 to 3.5. Letter D, approximate the distance traveled from the second hour to the 5th hour. So if we're going to go from the second hour, let's erase this. Let's get rid of that. So for letter D, we want the distance traveled from the second hour, so 1, 2, to the 5th hour, 3, 4, 5. So we're looking for this region right here. So that would be the integral of 0, not 0, 2. 2 to 3.5 v of t dt minus, remember forcing that negative area to be positive, 3.5 to 5 v of t dt. Like this region here is 1, 2, 3. That would make 3, about 3.5. So the distance traveled there would be 3.5 miles, and then 1, 2.5 minus negative 2.5. That was distance traveled, yes. Okay, so 3, 4, 5, so 6 miles. And lastly, when is the position function concave up? Now remember, this is the velocity graph, so the position function would be concave up whenever his derivative is increasing. So the first derivative, the velocity, is increasing from 0 to here, and I'll figure that in just a second, and then from here to here. So from 0 to about 2.5, so concave up from 0 to 2.5, and then concave up again, so 1, 2, 3, 4, 1, 2, 3, 4, 4.5 to the end of the graph, we'll call it 6. Okay, and so again, the reason that the position function is concave up is because velocity is increasing in that interval. That's just a review of things that we already know from our past. All right, let's get into today's lesson. We're going to continue finding or evaluating definite integrals. We're going to continue doing that geometrically, and we're going to do it using Riemann sums. And Riemann wants us to use rectangles. There are basically 3 ways to evaluate a Riemann sum. There is a left endpoint approximation, a midpoint approximation, and a right endpoint approximation. Let's take a look at number 1. The symbol, this definite integral, stands for the definite integral from a to b. By counting the squares, find an approximation from 2 to 14. And we could do that. I'm not going to take the time to count the blocks because that's a prior lesson. Let's jump into number 2, which is now asking us to use rectangles. It says find an estimate for f of c. We're going to go from 2 to 14. We're going to put in 6 rectangles. Now, the heights of the rectangles are what are determined by a left, right, or mid. So it's the height, so we can do a left endpoint approximation, a midpoint approximation, or a right endpoint approximation. And what kind of approximation we're doing is what determines the heights of the rectangles. So in this case, if you'll take a look, if we're going to put in if we're going to put in 6 rectangles, notice that they're telling me that they want an approximate, if you look at x equal to 3, the y value, the output is about, let's call it, I don't know, 18, could be 19. So they're telling me that the first rectangle is going to be a midpoint approximation, and it's going to be that tall. Remember what I just said is that it's the approximation, whether it's left, midpoint, or right, that determines the height of the rectangle. All right, then we're going to go to 5. So when we go to 5, which is between, obviously, midpoint between 4 and 6, that's about height of 11. And that determines the height of the second rectangle. So that's midpoint number 2. Then we're going to go to 7. That's about 15. And that determines the height of the third rectangle. That's midpoint number 3. Then we're going to go to 9. That's about 25. That determines the height of the fourth rectangle. Notice how I'm drawing those. Then we're going to go to 11. That's about, I'll call it 38. And that determines the height of the next rectangle. Not quite the middle, but you get the idea. Then we're going to go to 15. That's about 45. And that determines the height of the last rectangle. Now you can look at the rectangles. Mine's not drawn perfectly. If I had straight edge and really taken my time, you can see that the approximation appears to be, well, there's some places where you have some overage, like right here. We over-approximate, and we over-approximate here, but then we under-approximate. So midpoint is giving us a pretty good approximation and collecting that area without being too much or too small. Now these, we have 6 rectangles, rectangle number 1, number 2, number 3, number 4, number 5, and number 6. And we're simply going to find the area of those 6 rectangles as an approximation of the definite integral, the area under that curve. So these were the heights of all of my rectangles. And then notice that I have a common width. It's 2, 2, 2, 2, 2, 2. So the width of all of my rectangles is a common 2. So I'm going to multiply length times width. So the area of rectangle number 1 is 36, 22, 30, just doing length times width, 50, just doing straight across, if you're wondering where I'm getting these numbers. Let's see, what do we got here? 38, 76, and 90. So that's the area of rectangle 1, 2, 3, 4, 5, and 6. So if we add those up, 6 and 6 is 12, 14, 3, 4, 5, 6, 7, 8, 9, 14, 14, and 7 is 21, 21 and 9 is 30. So about 304. And there are no units on this. They just asked us to evaluate the area under the curve. So my approximation of the definite integral from 2 to 14 of f of x dx, approximately 304, and this was a midpoint approximation, meaning that the heights of the rectangles were determined by midpoints. All right, now we're going to do the same problem, except for this time we're going to use a different approximation. We're not going to use a midpoint. So let's take a look at the next problem. I believe in your packet there is another graph of this. If you take a look, you might have to flip a page or two. But in problem number 5, they're asking us to accomplish the same thing, approximate the area from 2 to 14 f of x dx. They want us to use rectangles, but now take a look at the x values they're using. 2, 4, 6, 8, 10, 12. So we're starting at 2, stopping at 14. So sectioning off that region. But notice, over here, they stop at 12. They don't use 14, and 2 is the leftmost bound. It's on the left, so this is a left endpoint approximation. And in most cases, they're going to tell you what kind of approximation to use. You don't have to guess. So in our left endpoint approximation, they tell me to go to an x value of 2. Now notice what I'm doing. That determines how tall my rectangle is, and I draw it from left to right. I go to the graph, I go to 2, and that gives me a height of about 20. Now I'm going to go to 4. I'm going to go up to the curve. That's left endpoint number 2, and it determines the height of rectangle number 2, and that's about 15. I'm going to go to 6. I'm going to put a point on the graph at 6. That determines the height of rectangle number 3, which is about 12. I'm going to go to 8. I'm going to put a dot. That determines the height of the 4th rectangle. I go from left to right. And that's a height of about 20. I'm going to go to 10, put a dot. That determines the height of the 5th rectangle. That's about, we'll call it 32. I'm going to go to 12, put a dot. That determines the height of the last rectangle. And that's about, well, let's call it 44. Now take a look and notice that in this region I have an over approximation, over, under, 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 under. So this seems to be, appears that it's going to be under the actual value of the area. This is just an approximation strategy. We'll get to some exact strategies later. These are the heights of my rectangles, and they also again have a common width. If they don't have a common width, you have to calculate the areas independently. So the common width of 2. So this time I'm just going to add up all of the heights. So 4, 5, 6, 7, 8. 8 and 5 is 13. 2, 3, 4, 5, 6, 7, 10, 143 multiplied by the common width of 2. I could have calculated the areas individually like I did before and then added. In this case, since they had a common width, I added all of the heights and multiplied by 2. So that gives me 6, 8, 286, which you can see is lower or less than the approximation that we had with the midpoints. So this is just another approximating technique using rectangles instead of counting blocks. It gets a little more precise. And then in your homework, you're going to be doing some with tables instead of graphs. So let's take a look at number 2. Now I'm going to do problem number 2, but I'm going to change the problem. Notice that in this problem it tells me to approximate the revenue using 6 trapezoids. Well, we haven't learned the trapezoidal rule yet. We're going to learn that a little bit later. So I'm going to change this problem just for the purposes of an example. Don't change this on your paper because you're going to need this homework problem. So we're going to do 6 rectangles, and let's do a left endpoint approximation. Again, I'm giving you that. That's something that's given, not something that you have to guess or figure out for yourself. So we're going to start at 1987. We're going to stop at 1993. So I like to just put rectangles on the top. So from 87 to 88, from 88 to 89, from 89 to 90, from 90 to 91, from 91 to 92, and 92 to 93. That way I can see that I have 1, 2, 3, 4, 5, 6 rectangles, which is what they were asking me to do. Now we're going to approximate the definite integral from 1987 to 1993. They don't really give this function a name, so we'll call it f of x dx. Now in this case, take a look at my x values. They change by 1, so 87 to 88, 88 to 89, 89 to 90, 90 to 91, 91 to 92, 92 to 93. So I do have a common width of 1, and you always have to check that and don't assume that the width will be in common. So there's my common width. Now remember, I'm using a left endpoint approximation. So that tells me start with the leftmost y value, because we're going to get the heights out of the y values. So the leftmost endpoint is 58.5. So the height of the first rectangle is 58.5. The height of the second rectangle is 27.5. The height of the third rectangle is 16.9. The height of the fourth rectangle is 25. The height of the fifth rectangle is 54.1. And the height of the last rectangle is 102.5. Now remember, there were only 6 rectangles. We don't use the 170.2 because that is on the right-hand side. It's not a left endpoint. So we have 6 rectangles. And then all you would do to get your approximation is to add those values and multiply by 1. All right, I'm going to do this problem one more time, except for this time I'm going to do a right endpoint approximation. So I'm going to get rid of this, just so you can see the difference. I can do a right endpoint approximation. Still going to have 6 rectangles. Again, that's also going to be told to you in the problem how many, or most times, how many rectangles you're going to use. We're going to use 6 rectangles, and we're going to do a, let's change colors here. We're going to do a right endpoint approximation. Now, the width of the rectangles is still a common 1. You can see that, but when we do a right endpoint approximation, 58.5 is not on the right-hand side. Remember, look at the rectangle. This is the left, and this is the right of the first rectangle. So the height of the first rectangle is 27.5. Then when we go to the second rectangle, let's change colors here. The second rectangle is here. So we go to, so this is the first one was right endpoint number 1. Now on the second one, this is right endpoint number 2, or the height of the second rectangle, which is 16.9. And then we get 25, add 25 for the height of the third, 54.1 for the height of the fourth, 102.5 for the height of the fifth, and then this time, 170.2 is the height of the sixth rectangle. Again, you would add those up, multiply, and that would give you an approximation of the area under that curve, even though you don't know what the curve looks like. It's just the best approximation you can get from the data.